In this section, we talk about a concept of Fourier series. Suppose we have a function f, equal to x squared. Of course, you can change this function to any other functions, like fx equal to x only, or fx equal to 25 x squared. Such and such, or fx equal to x squared plus 2x and minus 5, something like this. So this function can be arbitrary. Now the concept is this arbitrary function can be expressed in terms of the sine function. This is actually a very crazy idea, a very very crazy, because why? Because sine function is a periodic function, but x squared is not. So now you tell me that x squared equal to some sine function, sum it up together. What you mean? See, x squared not equal to 10x. It is obvious. For example, you have x squared. You cannot say that x squared equal to 10x, or x squared equal to 5x. Of course, it is wrong, right? In the same way, x squared, for example, x squared, if you say that x squared equal to sine 2x, of course it is incorrect. Or x squared equal to sine 2x plus sine 5x, such and such. Of course, it is incorrect. But now, the concept of Fourier series tell you that x squared can be expressed as a infinite sum of the sine function. So it is a quite magic. Quite a magic. Now, let me show you the key point. The key point is, you can write down such kind of mathematical expression, but the coefficient A1, A2, A3, A4 is undetermined. If you can find out the concrete value of A1, A2, A3, A4, then this expression is legal, because you can find out the digital number of this coefficient. What else can anybody say? If you cannot, you write down this mathematical expression, but the coefficient are unknown, cannot be determined, then this equality is doubtful, right? But now if you can find out the coefficients, A1, A2, A3, A4, A5, such and such, then this equality is confirmed. Now let us tell you how to compute the coefficients. For example, we want to get A2. Finally, we will get A2 here, right? Let me show you in detail. If we want to compute A2, finally we will get this. We compute A2, and then what we do is we multiply the left-hand side and the right-hand side by the same function. See, this function, sine 2 pi x over L, sine 2 pi x over L, sine 2 pi x over L, same function, right? So this equality doesn't change. The equality still holds because you are multiplying the left-hand side and right-hand side by the same function. Now, after you multiply this term and this term, you get this one. This term and this term, you get this one. This term, you get this one, right? And this term to get this one. Once you have done this, you can integrate the left-hand side and the right-hand side together. It doesn't change the equality too, right? Because we are doing the same mathematical manipulation. So we just integrate the left-hand side from 0 to L. Right-hand side from 0 to L, 0 to L, 0 to L. Such and such. And we put f x equal to x squared inside. Okay, this term is okay. Done. And how about this term? And I tell you that this term equals 0. Why? Because sine pi x over L times sine 2 pi x over L integrate from 0 to L equals 0. This result has been proved in the previous example, okay, in 1.4.1. Okay, here, sine 2 pi x over L, sine pi x over L, integrate from 0 to L equals 0, right? This is called the orthogonality of eigenfunction, okay? And this is the general formula. If in this formula we have n and m are not equal, n not equal m, and m here, then the integration will give you 0, okay? This has been proved by such kind of calculations. So sine 2 pi x, sine pi x, when they multiply together, integrated from 0 to L, will give you 0. Likewise, sine 2 pi x, sine 3 pi x, integrate from 0 to L, will give you 0 too. Okay, so according to the previous result, we have this equals 0. And this equals 0. And also, this part, the rest, all the other term equals 0. The only non-zero term is this one. Because we have 2 pi over Lx here. Because we are tying, see, 2 pi equal 2 pi. So here, this term after the integration will not be 0. But pi and 2 pi are not the same. So the integration will be 0. 3 pi, 2 pi are not the same. The integration will be 0. 4 pi, 2 pi are not the same. The integration will be 0. But here, 2 pi are the same. So the integration here not equal 0. Okay? So in this way, this term drops out. All this term drops out. So only A2 remain. Okay? So finally, we can obtain the mathematical formula for A2. Okay? For convenience, I tell you that the integration of this function will give you a simple formula like L over 2. Why? Because here, if you integrate this function, you use the famous formula to turn it from sine square to this one. And then this is a constant term. The integration is easy. This is a cosine term. The integration is also easy to get this one. And you put the upper bound and lower bound inside, you get L over 2 directly. So this is L over 2. Okay, and then we move L over 2 to the left-hand side here to get A2. This is the final result. Now, see, if you can get A2, how come you cannot get A1 and A3 and A4? You see, in the same way, in a similar way, we can get A3, A4, A5, A6, right? The same thing. You just multiply by, if you want to compute A3, you just multiply this by 3, right? Use sine 3 pi x over L. So, if we can get A2 like this, so we just can just generalize this term to this term. A2 generalize from A2 to AN. And we change the 2 here to N. Okay, then we are done. Okay, A2, AN, 2, N. Okay, so in this way we can get the general formula to the coefficients of the Fourier series, AN. Okay, it means that if you put n equal 1 here, we get A1. N equal 2 here, we get A2. N equal 3 here, we get A3. N equal 4 here, we get A4. So all the coefficients A1, A2, A3, A4 can be computed by this formula. So the equality here is legal. Okay, there's no problem at all. Okay, we can even get the digital number of them. Okay, in this example, this is 13. Please correct here. this is 13. We try to compute the coefficients one by one. We have fx equal to x squared and then equal to a sine series, and then we have already get the formula here, 2 over L, and this one is just the same as the formula before here. Now we perform the integration step by step. Here this is x squared times sine function. So what we should do is we use the old technique like u dv equal to uv minus v du, right? Such kind of technique have been introduced to you in the course of differential calculus. This technique is called integration by part. Okay, integration by part. If you cannot remember this technique, please go back home and then review, do some review about this technique by looking at the books of differential calculus or any book of engineering mathematics, something like this. Okay, so from integration, from the skill of integration by part, we use it twice. Once is not enough because we have x squared here. We use it 2 times, twice. Okay, and then u dv v du, we get this one x squared turned to x, and then again u dv v du, we can turn the x out. Finally, we can obtain this result. I repeat, you use u dv and v du transformation techniques twice, and then you can get this one. Okay, do it by yourself. If you have trouble in understand this, you can also ask me in the class. But I strongly suggest you to figure it out by yourself. Once you have done this, you get this one, and then you put the upper bound arrow and lower bound 0 inside here. I do it one by one. Arrow, x equal L here, x equal L, this one. Okay, x equal L, x equal L is this one, because this is L and L cancel out, so n pi. Okay, and then this one copy down here, but x turn to L, and this one L cancel out n pi. Now the lower bound, x equals 0, put it here 0. X equals 0, put it here 0. 0. Okay. Now after this, we also say that this term equals 0 because this n pi, sine n pi equals 0. Cosine 0 equals 1, and then cosine n pi equals minus 1 with n power. Okay, and then we put the result like this, and then after we grouping the terms, okay, this term and this term, they have the common term here, this one and this one, like this, and then we get the final result. Okay, once we get that, we get an, we can compute a1, a2, a3 without trouble. Now n equal 1, we get a1, and then we put 1 here. Okay, 1 here. Okay, if n equal 1, this minus 1, and then 1 here. So we get this, and then once we get this, is minus 2, and then we have minus 4, and then such and such. Do it by yourself. And then n equal 2, n equal 2, we get a2, and then n equal 2 here, so it can become plus 1, but plus 1 and minus 1 cancel out to each other. We get 0 here, and then n equal 2, we have 2 here, and finally we get this. And then now n equal 3, n equal 3, we put 3 here, 3, put it here, right? And then this 3, so this is minus 1, okay? And this 3, this 3. Okay, after after we grouping the terms, we get this formula. So A1, A2, A3 can be obtained without trouble. So we can write this function fx equal to this Fourier series. Okay, this is A1, this is A2, this is A3. Okay, so x squared indeed can be expressed as a sum of sine functions. Don't doubt about this. Okay, it is a magic, right? Okay, x squared expressed as a sum of the sine function. Okay, one more example. For example, we change the function fx to minus 10x here, and then the Fourier series turn to Pn sine n pi x over L. This one is just the same as before. Huh? See here, x squared equal to an sine something. Huh? So this dx should be cancelled out. Huh? This dx should be cancelled out. Okay, no dx here. So here x squared turn to minus 10x, and an change to Pn. Everything is the same. So the formula Pn is like this, because the formula of an, the formula of an is like this. An. Now we change an to Pn, and fx equal to minus 10x. Okay. So once we have done this, we get this result, and then we perform the integration here. We just put it here, and then we perform the integration using the technique u dv equal to uv minus v du. We get this, and then once we get this, we put the upper bound x equal L here, x equal L here, x equals 0, put it here, x equals 0, put it here. Okay, and then finally we get this. So we can have the mathematical formula for Pn, and then when we let n equal 1, then we get P1, n equal 1. And then we let n equal 2, we get P2, n equal 2, okay? And then n equal 3, okay? N equal 4, such and such. So finally, we can put this P1, P2, P3, P4, P5 into this expression to get this one. Minus 10x equal to this one times this sine series. Okay? 1, 2, 3, 4, 5, or infinitely many terms. So in this way, we had already used two examples to illustrate the idea that if you have an arbitrary function fx, then you can express this function as an infinite sum of the sine function. Now look at this example. This example come from the problem of beam. We consider a beam. This one, beam. This beam subjected to some loading here. Okay, the normal stress sigma yy equal to minus 10x, and then the shear stress equals 0. Here, normal stress and shear stress equals 0 at y0. At yx, we have this. So y0, normal stress equals 0, shear stress equals 0, yh on the top. The normal stress is this, the shear stress is 0. And then using the result, we will study later. We will have this one, this. This called the phi called the stress function. The stress function of this beam can be obtained like this. Okay, this is a Fourier series. See, sine lambda n. What is lambda n? Lambda n is this, n pi over L. Okay, so this one is just like this. So this is a sine function. Now Pn change to a function of y. So it looks a little bit clumsy because it is quite lengthy, but in fact it is only a Fourier series. Okay, sine n pi x over L times a function of y. Okay, this is called the stress function of the beam. Now, from this stress function, we can compute the normal stress. Okay, we differentiate this phi with respect to x twice, and then differentiate it to x twice. We get this one. The y function is just the same because we are only differentiated with respect to x. So we only change here. Okay, the rest will be the same. And I tell you, I make some mistake. The differentiation here with respect to x twice will give you the normal stress, sigma yy. So don't write phi yy here. Change it to sigma. Sigma means that the stress, sigma yy. Okay. In the same way, this should be sigma xy. This is the shear stress, sigma xy. Okay, equal to minus phi differentiation with respect to x and y. Okay. Now once you have changed this sigma yy, sigma xy, we can put this one into here to get this. This one means that we differentiate phi with respect to x, so sine become cosine. And then differentiate y here. This one, cosine, becomes sine. Hyperbolic cosine become hyperbolic sine. Hyperbolic sine become hyperbolic cosine. And this one, y times hyperbolic cosine become two terms. And this one, y times hyperbolic sine become two terms. Okay, in this way, we have the stress function. By differentiation, we get the normal stress sigma yy and the shear stress sigma xy. Okay, once we have got this, we can make use of the boundary condition to compute the unknown here. See, we have four unknown: an, bn, cn, dn. Right? We have four unknown. So how many conditions are required? 4. Okay, 4 unknown solved by 4 equations, right? 4 conditions. Okay, we have 1, 2, 3, 4. 4 unknowns. Okay, now we have 4 conditions. 1, 2, 3, 4. Understand? 1, 2, 3, 4. Okay, now let us calculate an, bn, cn, dn step by step. In the first step, we make use of this boundary condition, sigma yy equals 0 at y equals 0. This one. It means that at y equals 0, sigma yy equals 0. Okay? Okay, sigma yy equals 0. 0, okay? But sigma yy is what? Sigma yy, y equals 0. Sigma yy, y equals 0. So this one will be the same. We put y equals 0 here. 0, 0, 0, 0. So this one is 0. This one is 0. Drops out. We have this one 0. This one equal 1. Understand? We put sigma yy. We put y equals 0 into sigma yy. Once we get this, we have this an, bn, and 2 0 here. Understand? And then this equals 0. So this equals 1. So we have this one. This one is just this one. Okay? And this one is a psi series, but it must be 0. So what else can be true? Can be chosen? Only an equals 0. So because the summation of this psi function is 0, so the only possibility is this an equals 0. Okay. Now we have obtained an. How about the another condition? Just this one, huh? At y equals 0, shear stress equals 0. Here, this one. This is a shear stress. We put y equals 0 here. 0, 0, 0, 0, 0, 0. Okay? And then once we have done this, we have this one. Okay? And then hyperbolic cosine 0 equal 1. Hyperbolic cosine 0 is equal 1. Hyperbolic sine 0 equals 0. So the only term remains are Bn and Cn, like here. Okay? We copy this line into here. Now, this is our cosine series. Okay? But the result is 0. So the only way that this equality holds is that the coefficient must be 0. It means that this one equals 0. So we have Cn, this one equals 0. So Cn equal to minus lambda nBn. Okay? We have the second conditions for the coefficients. Now, two more conditions. Besides of this, we have this one. We have y equal h. Y equal h. The shear stress equals 0. Okay, this one. Y equal h. Shear stress equals 0. Shear stress. Now let's look at the formula here. This is a shear stress. Now we put y equal h. H, 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 h. Once we have done this, we get this one. Okay? And then an equals 0. An equals 0. Okay? And also Bn, just the same. Cn equal to this one. Cn equal to this one. So, and we have Dn. So the only unknown constant are Bn and Dn now. Cn have been cancelled out, have been replaced by Bn. So only Bn and Dn. Bn and Dn. Okay? So we have one condition for two unknown. So we need another one condition for these two unknown, Bn and Dn. Okay, let us consider the final condition here. At y equal h, sigma y equal to minus 10x. Okay, y equal h, sigma y equal to 10 minus 10x. This one, but this one equal to this. According to example 14, what is this? Let us take a look. This one. We have studied this example before. Pn. What is Pn? Pn is here. Okay. P1, P2, P3, P4, P5, and fx equal to minus 10x equal to this one. Okay. So this function has been expressed as a Fourier series successfully. Okay. So Pn are known. Okay. Pn are not unknown. Okay. Pn is given. Now Pn are given. Now we have this, and also sigma y equal to this one. Why? Because at y equal h we have sigma y. Let us look at here. Why? Sigma y. Sigma y. Y equal h. H. Once you have put y equal h, and then we get this. This one. Okay? And then an equals 0 according to this one. An equals 0. Cn equal to minus lambda n bn. So the only unknown constants are bn, bn, and dn, right? Only two unknown constants. Okay? And then, see, now is the key point. Huh? This is the psi function. This is a phi function. They are the same. So in order that this equality holds, this coefficient Pn must be equal to this one times this one. Understand? Because here psi equals psi. So compare the coefficient. Pn equal to this one times this one. Understand? So we have this one. Minus 10 equal to this and equal to this, and Pn equal to this times this. Pn equal to this times this. Understand? And then this is equation star 4. This Bn dn, Bn dn, one equation. Another equation is, sorry. Very good. This is a equation Pn equal to Bn dn, right? One equation for two constants. Another equation is this one, star 3. This one, star 3. Here we have another, conditions. This one. So star 4, star 3, we have two conditions. Of course, we can solve for two unknowns. Okay, we can obtain Bn and Dn without trouble. Let us look at the detail. From star 3, we have this, so we can express Bn in terms of Dn, and this one means that we move our term from here to here, and then divide this one, okay, and then move this term to the here. So we have Bn equal to this one, and then after some regrouping term, we get this one. So Bn equal to this. We put this Bn back to star 4. Bn, put it back to here, and then we solve for Dn. Putting star 3 pi into star 4 yields this one. So Pn, this one equal to this, equal to this one. Bn equal to this and this. Now only Dn remain. So we can express Dn in terms of Pn. Okay, and Pn is what? Pn is this one. Once now we have obtained Dn. Once we get Dn, we can get Bn. Dn is done. Is complete. We can calculate Dn according to this formula. This can be calculated. Pn can be calculated. Now Dn can be calculated. Now we can calculate Bn by this one, by this formula, or by this formula. Dn is given, then Bn is given. Now, after Bn is obtained, we can calculate Cn according to this formula. If Bn is given, then Cn can be obtained, and then An is obtained too. So Dn, Bn, Cn, An. Finally, we get all the coefficients. Okay, what will be the point? The point is, see, in this example, this is called the stress function. Okay, for the beam problem, you have the stress function phi here, expressed in terms of a Fourier series with four unknown An, Bn, Cn, and Dn. But now, An, Bn, Cn, and Dn can be determined from the boundary conditions. Okay, so we can compute this function without trouble. With this function, we can calculate the the normal stress sigma yy, shear stress sigma xy, and also sigma xx2. We will learn this knowledge later. Okay, so the basic idea here is this. If we are dealing with a problem of beam or other plate, something like this, or circular plate, elliptical plate, we write down the boundary conditions and then solve some equation to get the stress function. Once you get the stress function, you determine the unknown constant in this stress function by the boundary conditions, and then you get phi. After you get phi, the stress function, you can compute the stress components, sigma yy, sigma xy, and sigma xy, sigma xx. Okay, this is the basic idea of how one can use the Fourier series to solve the problems in solid mechanics.